So great. Now, apparently we are quite a few now. I don't know, I missed the screen. Yes. Yeah, so we are quite a few now, and welcome everyone to the 31st webinar in this discussion series on tipping elements, the notion of reversibility and abrupt changes in the Earth system. My name is Beatriz Arellano Nava. I am a postdoctoral research fellow at the Global Systems Institute in the University of Exeter. I have some previous experience working with early warning signals for tipping points in the North Atlantic, particularly those associated with the North Atlantic subpolar gyre. So thank you everyone for joining one more episode of the Tipping Points discussion series. The goal of this discussion series is to advance knowledge on tipping elements, support efforts to increase consistency in treatment of tipping elements in the scientific community, and also develop a research agenda and design joint experiments and ideas for a tipping point modeling intercomparison project, TIPMIP. And the networks behind this series are the Earth Commission, AMOC, which is the Analysis, Integration and Modeling of the Earth System project. Also, both AMOC and the Earth Commission are hosted by Future Earth. Also, it's the Safe Landing Climate's Lighthouse activity of the World Climate Research Program. And this event is co-organized by the International Institute for Applied Systems Analysis and the Potsdam Institute for Climate Impact Research, as well as the Global Systems Institute at the University of Exeter. And having said that, now we are moving on to the topic of today's discussion, which is the AMOC tipping point, impacts on climate and extreme events. So we all know that the Atlantic Meridional overturning circulation is a crucial part of Earth's climate system and is responsible for redistributing heat around the globe, and in doing so, it influences the weather patterns. And recent studies suggest that this circulation system of ocean, or this vital system of ocean currents, could be approaching a tipping point. And this could have dramatic impacts on climate and extreme weather events worldwide. So today, our speakers are going to be discussing new insights on AMOC tipping and links to extreme events. So now I am just going to mention some important rules to follow during these talks. So please, if you have a question, just drop it in the Q&A box, not in the chat, please. And both of our speakers will present before the Q&A session. And during the talks, feel free to pose questions and indicate to whom your question is directed by using the Q&A feature, which you can find at the bottom of the Zoom window. And everyone can also vote to prefer a question, so we can ask the most voted questions to our speakers. So then we will get to these questions in a discussion session following the presentations. And also following the event today, we will post the recording and the slides on the Tipping Point series Confetti webpage, so they will be accessible in the future. So thank you again to both of our speakers. Now we can start with our first speaker. So our first speaker today is Dr. René van Western. René is a postdoctoral researcher at Utrecht University, specializing in physical oceanography and climate dynamics. His current work focuses on tipping points in the Atlantic Meridional overturning circulation, AMOC, and broader Earth system changes. He completed his PhD in physical oceanography at Utrecht University, where he investigated ocean processes in the Atlantic sector. René has contributed to several influential publications, including studies on tropical cyclone responses to climate change and the impact of ocean eddies on global sea level projections. So thank you, René, for being here today, and this space is yours.
Yes, thank you so much. I will share my screen with you. And I hope that everybody can see this now. Yeah, so thank you so much for the introduction. So I'm going to talk about AMOC tipping events under different forcing scenarios. And to get everybody on the same page, so the AMOC stands for the Atlantic Meridional Overturning Circulation. And you can see a schematic here on the right of this panel. And the AMOC transports massive amounts of heat and salinity through the global ocean. And so the red arrows here are surface currents, so in the upper 1,000 meters of the ocean. And eventually it streams all the way up to the higher latitudes around Greenland. And there, very important water mass transformation processes takes place, and that actually causes sinking at the higher latitudes. And eventually, a deep cold undercurrent flows southward again. So you have this very big conveyor belt image also depicted here in the top left panel of the schematic. And what we now know, for example, from proxy records, is that the AMOC was a tipping element in past climates. And there is this risk that it can go from a very strong state, shown here before, to a substantially weaker state. And this causes less heat transport towards the higher latitudes, and especially for northwestern Europe. But what do we know, for example, from climate model simulations, is that the AMOC strength during the 21st century is projected to weaken. So here you can see on the horizontal axis the time starting from 8050 up to present day in 21st century. And on the vertical axis, you can see the AMOC strength at 26 north. So this is a suite of 25 different SIEM6 models and also with their SSP scenarios. And the purple curve here is observations along the rapid array. And what we are expected to see under future climate change is that the AMOC is declining, and there is not that much variations between the different SSP scenarios up to 2050. And in the second part of the century, you see more deviation. And for a stronger emission scenario, you see a general stronger weakening of your AMOC. However, what is now, of course, quite a hot topic of debate, will the AMOC collapse or will the onset of the AMOC start to collapse during the century? Because if you take the multi-model mean, the AMOC strength remains fairly strong. It remains, for example, above 10 sverdrups. And I think a lot of people could argue that this is not a collapse. There are also some SIEM6 models, they go almost down to 0 sverdrups. You can see it in the violin plots at the right. So we are interested, is the AMOC able to collapse and where does this come from? And then we can go back into literature very nicely. And the first depictions that the AMOC was a tipping element that originated from the famous Stommel model designed in 1961. And it simply consists of two different boxes. They communicated with each other via this volume transporter indicated here by psi. And with this very simple model, you can come up with an analytical solution of the different kind of steady states, which are shown here on the right plot. So on the horizontal axis, you see your freshwater flux forcing parameter. So that's your tuning parameter where you can switch between different regimes. And on the vertical axis, you see your circulation strength. And there are now two different states, which are stable, which is the AMOC on state, and the reverse state, which is the AMOC off state. And the dashed line here is this unstable branch which separates both basins of attraction. So this already shows bimodal behavior. And if you then go up in the model hierarchy, so for example, with more complex models, so this is an AMOC box model, but now with 5 different boxes, also with an overhead atmosphere, you can also still find a similar kind of bifurcation diagram. So you still have an AMOC on branch and also a collapse state and a weak state. And if you go further into time, you're having and also in the model complexity, you are having these intermediate models of complexity, which show this different kind of bistable regime. So this is this paper from Stephen Ramsdorff back in 2005, where you see that a lot of different kind of models show this AMOC on state and AMOC collapse state. Then if we go to the coupled GGMs, so this is a CMAP3 version from UA colleagues. They've also conducted this freshwater flux forcing experiment, a so-called hysteresis experiment, in which you slowly increase this freshwater flux forcing, also similar as before. And if you then follow, for example, the black trajectory, which is in increasing freshwater flux forcing, you see that the AMOC reduces in strength. And if you then reverse the freshwater flux forcing again, followed by this red graph, then you see that the AMOC follows a different kind of trajectory. So this really nicely depicts that you are having this hysteresis behavior in your AMOC, which was still very interesting. But there was no really abrupt collapse. If you look at a black graph, it is quite linear. So that was also what we found very fascinating. So why is there not such a abrupt collapse found, for example, in these simple box models? Other experiments also shown this kind of multi-stable regime. So this is from Macking et al., where they have this eddy permitting model, so a very high ocean resolution. And they also show this, that the AMOC stays at the relatively low values. It remains at 5 swerdrups for about 400 years. So it's also very impressive. And if you go to the latest climate model simulation, so this is CMIP 6, there's also this indication that the AMOC can remain in a quite low state. So this was done with a pulse forcing experiments. So for example, if you look at the lower panel, you see that after 50 years, so that is the sine curve, the AMOC remains fairly stable at a very low and weak state. So there have been all these kind of indications. And what we have done quite recently is to investigate how this salt advection feedback can destabilize the AMOC. And to give you a quick reminder, so this is a schematic of the salt advection feedback. So this is at the top left, you have your surface equatorial water, which is relatively warm and saline. And in the top right, it is relatively cold and fresh. And the water in the top right is relatively heavy. It sinks and causes this clockwise circulation. And what we can actually do in these climate models is adding, for example, a precipitation anomaly or more land ice runoff from the Greenland ice sheet, which causes a precipitation anomaly indicated in plus, which causes a relatively fresher water indicated also by this plus, meaning that this water becomes lighter, here indicated with a minus sign for the heavy water. And this causes that the water tends to sink less, and this reduces, of course, your circulation strength, here indicated with a minus sign. And now this top right arrow, which transport relatively saline water from the equatorial regions to the higher latitude regions, this reduces in strength, which causes the surface in the North Atlantic Ocean to freshen even more. So this is a self-amplifying feedback loop. So this is the destabilizing salt advection feedback. And this, of course, is a runaway feedback mechanism and which causes the AMOC eventually to shut down. So what we have now done was doing this kind of experiments in a fully coupled climate model, so with a community Earth system model, where we apply this freshwater flux forcing between 20 north to 50 north, and we have a global surface compensation elsewhere. And we've done at a very slow pace, increasing this freshwater flux forcing value. And there are the results, where you see on the horizontal axis the freshwater flux forcing strength, and on the vertical axis the AMOC strength. And eventually you see after a while that the AMOC eventually abruptly collapses to a state of 0 swerdrups. The next step in this experiment was to do the reverse experiment, where we actually reversed experiment, lowering the freshwater flux forcing again. And then we saw that the AMOC recovered, and it follows a different kind of trajectory. So this is quite comparable to the results from you et al. I showed before. So this was a very impressive analysis, and you can also see that the AMOC eventually recovers up to 33 swerdrups. So that was a very strong overshoot, but that was also found with previous literature. And also to test whether these, like this, that there is no like a very long transient response during the collapse or recovery. We've actually determined also these so-called steady states, here indicated in blue. And we can really say that those are different kind of statistical equilibria of the system. So meaning that we have a very wide AMOC hysteresis regime or multi-stable regime in our community Earth system model. And we've also done even more statistical equilibria, really showing that the system is relatively stable up to the tipping point, and then it starts to collapse. And with these kind of experiments and also with these model simulations, we can analyze tons of different kind of interesting statistics and also see how the climate shifts. And maybe you've seen these kind of figures where here on the left, we show the near surface temperature, and you see a spectacular drop of the temperatures in your North Atlantic Ocean. And you also see it in the sea surface temperatures here on the right, where temperatures can go down to minus 20 degrees Celsius in the annual mean temperature. So that are like a massive shift in your climate. And what we further contributed is look at the different kind of contributions, how this AMOC collapse starts. So this is work from a PhD student, from Elion van der Borg, and he has analyzed all the different kind of contributions in this quasi-equilibrium experiment. So I'm not going to explain all the details, but this blue graph, that is the hosing. So that we are adding actually fresh water, which causes a linear response in your AMOC decline. But I would like to focus here on this black graph at the very end. And this is the salt advection feedback contribution. And you can see that at the tipping point, this contribution becomes very, very strong. From a theory point of view, it goes to infinity. And this is the salt advection feedback strength. And with this decomposition, we can actually link this salt advection feedback strength to this FOVS parameter. So that is the AMOC-induced freshwater transport at 34 South, which is shown over here. And the yellow shading here is the last 150 years before the AMOC tipping event. And what you can nicely see with this FOVS parameter is that there is first this minima in this FOVS value. So that is a indicator of the of the tipping event. But you can also see that the variance is increasing prior to the tipping event. So this connects very well to theory. But what is good to keep in mind that this FOVS parameter is only relevant when you're using equilibrium conditions, so meaning in this kind of setup. But like two main questions remain for us. So does this FOVS indicator still work in a high resolution ocean model? And does it also work under climate change? So these were still outstanding questions. So we contributed to the first one. So I'm happy to announce that we have actually have done these high resolution ocean model simulations. So that is shown here on the left in animation. And here on the right, you can see a low resolution model. So they don't have any active atmosphere. So they are really just like an uncoupled version 1. But now we can nicely compare the two different kind of configurations, in which in the left one, we have those ocean eddies, those beautiful swirls, while on the right, they are absent. But it is very interesting and worthwhile to conduct the same kind of hysteresis experiments with those different kind of settings. And I'm also happy to report that this paper was published yesterday in Geophysical Research Letters. So you can scan the QR code, or also afterwards when the slides are available, and then you can see what kind of experiments we have done with the high resolution standalone POP version of the model. But to give you a sneak peek, so here on the left, you can see the AMOC strength, and on the right, you can see this FOVS. And exactly the same thing is that if you increase your freshwater flux forcing, your AMOC eventually collapses in a strongly eddying ocean model. And this also confirms that the AMOC can collapse when you're having a strongly eddying ocean model. And if you then look at the right for this FOVS parameter, it also goes through a minimum. Its variance is also increasing prior to the tipping point. You can't see that very quickly from this figure, but we've also demonstrated that this FOVS connection still works over here. And then, of course, if you then look, for example, at the different kind of configurations between in high resolution POP and low resolution POP version, so high resolution again on the left-hand side and the low resolution POP on the right-hand side. So these are the overturning circulations. So this is for the AMOC on state. And if you then go to the collapse state for both of them, you see that they have a complete different kind of end state. So for the high resolution POP, we still have a weak residual of about 5 swirl drops. But for the low resolution POP, we have a complete and very classical reversed circulation. So this really surprised us that there is a very striking difference between both of them. And with these kind of setups, we can also look, for example, what the different responses are in this ocean-only configuration. So here I show you, again, the same kind of comparison, high and low. And here you see the sea surface temperatures, and you can see this beautiful fingerprint in the North Atlantic Ocean. So this is characteristic of this AMOC weakening. But also if you go, for example, to mixed layer depth, the mixed layer depth completely shuts down in the North Atlantic Ocean. And what is also very interesting, if you now look at the Southern Ocean, there is a complete and different opposite response between the high and low resolution versions. And this is due to the fact that ocean eddies are represented in the high resolution one, and this gives a very striking difference between both versions. And also for dynamical sea level rise. So again, the patterns are quite similar, but if you zoom in, for example, in the Gulf Stream regions, which is shown over here, there are a lot of interesting features going on. So there are small deviations in the path of the Gulf Stream. It is much better represented in the high resolution version. So we just did a first quick analysis on those simulations, and we are now investigating those more. So if you want to have all the details, I'm not able to answer them yet, but we're planning to investigate a lot of different aspects between those different kind of pop versions. So the second question we also had with the AMOC collapse can it also happen, for example, under a climate change scenario? And what we have done over here is we have different AMOC configurations. So on the left, we have with a constant lower freshwater flux forcing value, and on the right with a higher freshwater flux forcing value. And you see the AMOC strength in model years and also the temperature anomaly in the inset. And here we followed first the historical forcing. Then we've continued this with an RCP 4.5 scenario up to 2100. And then from that point on, we kept this forcing constant beyond 2100. And what you nicely see is that up to 2150, the AMOC fairly remains stable for both scenarios. But for the right one, the AMOC does collapse, while for the left version one, the AMOC does recover. And this actually nicely sees that you're for the same kind of forcing scenario, but with different sensitivity values for the AMOC. You can already see that the AMOC is much weaker in the right version. The AMOC eventually does collapse under climate change, and for the other one, it eventually recovers. But now we can compare those different two RCP 4.5 scenarios against each other to see what are the climate impacts under these different kind of scenarios. So here again, I show you these different scenarios. So on the left, you see the very classical warming. Everywhere you see that the surface temperature is increasing. Well, if you then look at the right one, where you have global warming and an AMOC collapse, you see this very strong cooling over northwestern Europe, while other regions are simply warming under climate change. And we can also look, for example, at a different quantity here shown for precipitation. So for the left one, there's generally an increase in precipitation due to Clausius-Clapeyron. But on the right one, you see the combined effects of that and an AMOC collapse. And in particularly, you see this shift of your tropical rainbows southward. So that is also very nicely captured under climate change and an AMOC collapse. And also to connect a little bit to the extremes, what was also in the title. So we can also look, for example, at extreme values. So we have daily average data available. And then we can do all these extreme analysis. So this is the PI AMOC on case. And if you then go to the future scenario, so this is specifically shown for the Netherlands, you see that the extremes under climate change can become less intense for the case where AMOC recovers, but it can also become much more intense when the AMOC does collapse and under climate change. But then this is, of course, specifically shown for Northwestern Europe, which is a region which is impacted quite a lot under an AMOC collapse. And part of this very intense cold extremes is due to the effects of the Arctic sea ice, which can extend all the way down to Northwestern Europe, shown here on the right panel. So this is the January sea ice extent for the one where the AMOC collapses on the right. And when AMOC does recover, you don't have any influence of the sea ice, which of course makes sense compared to the present day configuration. So that is only, of course, only temperature, but you can also look at different kind of quantities. So we've also looked, for example, at the dry season intensity between the two different regimes. So this is the increase in your dry season intensity. And if you compare both panels here, you see that the one with the AMOC collapse, the dry season intensity becomes even worse. So an AMOC collapse in combination with climate change amplifies the already expected dry season intensity. So that is the different kind of climate impacts we're currently investigating. And then the main question here is, so does this salt advection feedback still hold? The answer is yes. But unfortunately, you can't say anything with this FOVS parameter. So because the responses in this FOVS parameter under climate change is very transient, and then those quasi-equilibrium conditions do not hold anymore. So, but this FOVS value, its initial value sets actually your AMOC stability, because on the left, your FOVS is positive, which means that your AMOC is too stable. But on the right case, your FOVS starts as a negative value, which means that you have a destabilizing AMOC feedback. And this relation between this stable AMOC and very unstable AMOC that also appears in different SEAM6 models. So here on the horizontal axis, I show you the FOVS values, and on the vertical axis, you see this AMOC strength value. And if you then look at the black markers, those are results of 39 different SEAM6 models. There is this tendency in the SEAM6 suites where when you have a very low FOVS values, you are usually having also relatively low AMOC strengths. And of course, it's the other way around. So meaning if you are having a correct FOVS, a correct AMOC sensitivity, your AMOC is simply set too weak. So meaning that it is also in this unstable regime and it is more prone to tipping. And of course, we need to fix that with the next generation of climate models in CMIP 7. But with this new paper we've been working on, which we've submitted last week, we developed a new indicator. So that is a physics-based indicator in North Atlantic Ocean. And what with this new indicator, I won't explain all the details, but what we can actually show that this also works under climate change. So that is an improvement compared to this FOVS parameter. And we've also tested it for different kind of SEAM6 models, for which some of them also collapse up to 2300, here shown for this MRI model, where the AMOC collapses, and we can already predict that the AMOC starts to collapse by 2025. So that's a very powerful tool. But of course, we need to wait for the revisions for that paper as well. So to wrap up, hopefully I stayed in time, I'm not sure. But the main thing we've been working on is that we found AMOC histories as behavior in different kind of models, also in the CMIP 5 model. And we also find it quite recently in a strongly eddying global ocean model. But the exact role of ocean eddies, that remains a big question. And we see already a lot of interesting and new features showing up that the AMOC also remains stable at 5 swirl drops. And also under climate change is that depending on your initial conditions, your AMOC may collapse under climate change. But it is very good, good to reduce those model biases to get a correct AMOC sensitivity. And if such an event happens, an AMOC tipping event induces very disruptive climate change, and therefore we should avoid this at all costs. So thank you very much, and I'm looking forward to the discussion.
Thank you so much, René, for such a great talk.
You're welcome. Thank you.
Yeah, that was great. And now, if you have any questions, please post them on the Q&A box, because we will address them during the discussion session following the next speaker. And now it is my pleasure to introduce the next speaker, Dr. Anastasia Romanow. Anastasia is a research physical scientist at NASA's Goddard Institute for Space Studies, specializing in oceanography and climate variability. She holds a PhD in physical oceanography from Florida State University and a master's degree in oceanography from the University of Athens. Her research interests encompasses the meridional overturning circulation, ocean heat and carbon uptake, and their roles in the climate system. She also investigates air-sea fluxes in the North Atlantic and explores ocean and climate feedbacks in collaboration with global scientists. Anastasia is an adjunct associate professor at Columbia University and has held several postdoctoral and research scientist positions. Thank you, Anastasia, for being here, and the floor is yours.
Okay, thank you very much for the introduction, Beatrice, and for the great talk, René. It sets the stage for my presentation today, where I want to focus a little bit on new results that we have with our climate model, the NASA Goddard Institute for Space Studies Model E, and under different configurations of climate change and the sensitivity of the AMOC to this these conditions of forcing, different conditions of forcing. So please let me share my screen. Here we are. Let me know if you can see my screen. Okay?
Yes, okay.
Great. So I'm going to talk about cases of AMOC bifurcation tipping due to internal climate variability. And this is an outline of my talk. I'm going to give a little bit of a discussion along the lines that René just presented for the AR6 IPCC state of consensus with regards to AMOC. Of course, this is a little bit old now, back in 2021. Then I'm going to talk about an AMOC collapse due to greenhouse gas forcing and due to greenhouse forcing and internal variability. I'm going to talk about zero emission scenarios and different kind of scenarios than SSP, and the role of feedbacks and how extremes also can lead to AMOC tipping. And lastly, I'm going to make some comparisons with housing experiments that René just discussed. I want to point out in these simulations that I am doing, in all simulations, but the last ones, the last bullet point here, housing experiments, all my simulations, we do not apply any freshwater, external freshwater flux, but rather the AMOC collapses due to internal mechanisms of the system, which is some freshwater fluxes produced by the system together with feedbacks. Okay, so what is the state of the art? As René pointed out, we have, in CMIP6 models, we have a better understanding of AMOC evolution through the historical period. We have more measurements, longer time series from rapid MOCA, from OSNAP and other cross sections and transects in the world ocean. And we know that the AMOC has exhibited some internal variability, has large internal variability. What we know from climate models, CMIP6 especially models, compared to CMIP5, they show a peak that you can see here, a peak in the 1980s, and then a strong decline starting 1990s and thereafter, continuing into the 21st century. Now, the AR6 focused on this period of time of future climate, only the 21st century, but we will go a little bit further than that. And so what are the results, the main key points with regards to AMOC? That AMOC is expected to slow over the coming decades. There is low confidence that there will be a collapse before 2100, given all the parameters taken into account in the AR6 report. Due to surface ocean freshening, the major drivers of that AMOC weakening and perhaps collapse is the ocean surface freshening, which comes from meltwater from Greenland or from changing Arctic sea ice, even precipitation patterns changing over the warmer parts of the oceans. We have indirect signs of slowing of overturning, and that is an accepted notion in AR6. This one of those examples of signs of the slowing overturning is the existence of the delayed warming in the subpolar gyre, the so-called cold spot, or some people call it warming hole, where the warming is slower than the global average. And that's an indicator that the AMOC is weakening. But also another key finding of the AR6 is that models do not predict well the interannual to decadal variability in the AMOC. For example, they don't capture some of the large events of the order of 10 Sverdrup's weakening, like the 2011 weakening. Of course, they don't capture well, models don't capture well how this variability might be changing with climate change. So indeed, in the CMIP6 model assessment with regards to the strength of the AMOC weakening in the historical and future scenarios, we depended a lot on the Wager et al. Paper, GRL paper 2019. Here, all the different colorful dots are different models, the mean decline and the uncertainty of that decline in different scenarios, the historical, the abrupt scenario, SSP 126, 245, 370 and 585. And all these assessments end in 2100, which is kind of too soon because 2100 is very close to the time that we are right now. The NASA Goddard Institute model is these two brown dots that you can see over here, well, squares that you can see over here. We have among the strongest AMOCs and showing stronger declines than other models. But within the pack, as you can see, during the historical and the abrupt climate change scenarios. When this paper was published, the results from our SSP simulations were not available. Therefore, you cannot see the GIS model where it's placed on these diagrams. And I have to point out that we are here looking mostly at ensemble means. Yes, there is some kind of expression of the variance across ensemble means, which is an expression of the internal variability, but it's not very large. All right, now CMIP 6, as I said, looked at in detail up to 2100, the evolution of AMOC, but it didn't look beyond that. Even though there were proposed scenarios for SSP forcing beyond 2100, exchanging the forcings according to plausible scenarios. I'm pointing out here, for example, SSP 245, where they looked at an extended scenario where CO2 forcing slows down, doesn't completely reverse. Other scenarios, you have reversals of CO2 forcing, radiative forcing, but in the SSP 245, it just slows down and remains at high levels, but slows down significantly and only starts to decline after 2200. All right, so with the GIS model, now everything that I'm going to be showing is with NASA GIS model E. We looked at the AMOC collapse due to greenhouse gas forcing. We looked at all the scenarios, SSP 119 all the way to 585, including the reversal scenario 534 over, the overshoot scenario 534 over. And you can see them in different colors. This is the AMOC strength at 26 North, the rapid MOC array location. In most of these SSPs, all the way up to, in the first three, 119, 126, and 434, the AMOC recovers. In scenario 245, the AMOC seems to be remaining at a weaker, like 10 Sverdrups weaker, but still a constant. And then in scenarios 460, 370, and 585, the AMOC actually collapses. Collapses meaning that it is reduced beyond 80% of its initial value, initial strength. And the same picture we can see in the subpolar gyre of the overturning the subpolar gyre. In Z coordinates here, the AMOC strength also declines, and there is this difference of the difference of the AMOC strength in different scenarios. In the low forcing scenarios, the AMOC recovers. In the high forcing scenarios, the AMOC collapses, actually to zero. Apologies for the noise. It's New York street noise. Okay, so the AMOC collapse, now in the previous discussion, I showed you the average, the ensemble mean average. We run 5 to 10 ensemble members, and then we look at the variability between these ensemble members, but as an ensemble mean, and maybe the spread of responses around that mean. We don't look at individual scenarios, and that's what I'm showing here. This figure is exactly the same as before, AMOC strength at 48 North, all the scenarios again, but here I'm focusing beyond now 2200. You can see beyond 2200, we see the response of the SSP 245 scenario, where out of the 10 ensemble members, 8 ensemble members will have AMOC collapse, and 2 ensemble members will have 8 recover and 2 collapse. Now I want to take a moment to let that sink in. We are talking about one scenario, the same climate forcing, the same greenhouse forcing, the same, nominally the same variability, internal variability, but what we are seeing is in some of the ensemble members, the AMOC will weaken and then recover as the forcing starting to change and as the forcing starts to decline. But in two of the ensemble members, the AMOC will continue to collapse. Note that there is no external freshwater forcing added to the system in any of these experiments. So in the high scenarios, 370, 585, we see them over here. 370, 585, and 460, we see them over here. The AMOC collapses because of the greenhouse gas forcing. And in this case, the AMOC bifurcation is happening because of some internal dynamics that I want to discuss now. In order to understand what's the mechanism of collapse in this 245 scenario, we looked at the salt budgets because salt salinity is actually the driving process. The salinity changes the driving process for this the shutdown of the mixing in the subpolar gyre. And we looked at both Labrador Sea and Irminger Sea. In the GIS model, Labrador Sea shuts down very quickly, but the Irminger Sea is the one which stays active and provides dense waters and deep water, dense water volume to the North Atlantic deep water to be accounted as AMOC. Part of the AMOC, sustains the AMOC. So we looked at the freshwater forcing from different processes. For example, the sea ice melt, the glacial melt, the advection diffusion from below, and entrainment from below, and rivers, and evaporation minus precipitation. And we concluded through the analysis that is shown in this figure. You can find more information in the Journal of Climate paper. It's actually the sea ice melt, which is shown in this figure here, is the sea ice melt where the stochastic variability for all the processes is shown separately. The stochastic variability ratio is larger than 1, significantly larger than 1 in absolute value, meaning that it overcomes the forced response, which is shown in the top diagrams. In the Labrador Sea and in the Irminger Sea, as I said, we are focusing on the Irminger Sea, and we are seeing that the sea ice melt is actually the one that drives that freshening in the surface freshening in the Irminger Sea. That's responsible for the shutdown of convection and the decline of AMOC. Now, extreme variability, as I want to point out also that this sea ice melt comes from transport of sea ice, which is coming in through the Denmark Strait into Irminger Sea and melts there because the conditions there are warmer and therefore freshens the surface of the ocean. Now, these extreme events, extreme variability in the Arctic processes has been noted a lot recently, and there is a nice schematic from Overland 2024, where he is describing how natural variability can combine with storms, climate change, and the Arctic amplification to lead to a new type of extremes that we are seeing now already in the Arctic Ocean that we've never seen before. And these extremes can have huge ecosystem impacts and social impacts, of course. So basically what the schematic diagram of the process that is happening is that in the AMOC off case, what we have is we extend the sea ice transport into the Irminger Sea because of extreme events of that stem from the internal variability. So the internal variability can have some extreme years where the sea ice flux into the Irminger Sea will be so much higher, the melt there, and they will produce strong feedbacks with the overlying atmosphere, where we have a stronger warming hole, colder conditions, and that will reinforce the building up of sea ice. And that is where the AMOC off case, because the sea ice that comes into the Irminger Sea melts and shuts down convection. Whereas in the AMOC on case, we have the sea ice doesn't happen to extend too far into the Irminger Sea, and therefore the the ocean and the atmosphere are quite warmer, and the convection can resume or be maintained at healthy levels. So the role of feedbacks is critical. Internal variability alone cannot do it, but it has to be amplified by feedbacks. What are the feedbacks that are key in this area? First of all is the feedback that René talked about, the salt advection feedback. Now note that in our pre-industrial simulations, but also in these transient simulations, MOV is positive, always. It doesn't change a sign. MOV, the freshwater flux at the southern, at 33 South. It's always positive, which would imply a stable AMOC on case. But that is not the case. What we are seeing is we have the influence of other feedbacks like the ice albedo feedback and the ice evaporation feedback. What happens is that as the sea ice increases in the SPG, we have increased albedo, surface cooling, more sea ice buildup, and therefore that's a positive, reinforcing the AMOC decline. Whereas in the other case, we have again an AMOC decline will impose more sea ice increase, ice melt increase, colder temperatures, and less evaporation and more freshening, and that is also another positive feedback. So these are only two of other feedbacks. There are obviously more associated with the presence of meltwater into the in the North Atlantic, and these coupled feedbacks are not always captured in hosing experiments and also in standalone experiments. Now, this was the scenario SSP-245, which I have to mention, this is a very plausible scenario of future Earth because it takes us to 2 degrees warming by the end of the 21st century, and that is something, maybe 2.5. So that's something that we will probably face if the way that we are going. Here we are doing a different kind of scenarios. These are the zero emission scenarios. What these do is that we start from an emissions-driven, CO2 emissions-driven 1% scenario, and then we switch off the emissions at different levels of accumulated carbon in the atmosphere. So at 800 petagrams, this is this first red line, at 1,000 petagrams, etc. Of course, as we increase the amount of cumulative emissions to the atmosphere, we increase the warming. And so here we look at what happens when we switch off emissions at these different warming levels. On the right, you can see the response of the AMOC. In the lower warming scenarios, these first three, which are pretty much consistent with keeping to the Paris Agreement goals, the AMOC recovers. But when we go to the higher scenarios, the highest of all, the 2000, which is a dreary world, actually the AMOC collapses. But in the other two scenarios, where we didn't emit so much greenhouse gases, the AMOC will recover, but not always. In six experiments, in one of the 6 experiments in this green scenario here, one of the ensemble members will have a delayed response, a delayed recovery that will take about 100 years. And in the other case, in the higher scenario, only one will recover and all the other 5 scenarios will collapse. So we have now a possibility, we are counting the possibility of of having an AMOC collapse, even though the ensemble mean or the forced response may be favoring recovery. And again, we looked at what leads to these tipping points in AMOC. Tipping point, not abrupt tipping points, but slower change, leading to an AMOC off state. It's exactly the same as in the previous situation in the SSP-245 scenario. We see that extreme events, you can see them here in the ensemble mean, extreme sea ice coming into the Irminger Sea. This is a feature of our model. We have extreme sea ice coming into the Irminger Sea from the Denmark Strait, and that leads to the shutdown of the convection in some of the scenarios. In one scenario here, and in 5 out of 6 scenarios in simulations in the next scenario. So that allows us to build perhaps a picture of how the probability or the likelihood of the AMOC tipping is changing with the variance of that sea ice transport. Now, note this is our hosing. It's not a true hosing because we don't externally impose it, but this sea ice transport arises from the model interactions and the feedback interactions. And we see that in the lower warming scenarios, 1.4 to 1.9 degrees Celsius global warming levels, the variance of that sea ice transport is very low, and we don't have AMOC collapse. The AMOC collapse shown by the y-axis here is actually 0. But in scenarios above 2 degrees Celsius, 2.3 to 2.8, this probability, this likelihood now becomes non-zero and increases as we increase the external forcing. So its a schematic diagram would show here that as the variance of that sea ice transport increases, we have a higher and ever more higher possibility of one of the ensemble members escaping and going into the AMOC off well, or all of them going into the AMOC off well in the more extreme forcing case. So extremes can lead to tipping points. An AMOC decline, which is caused by a sea ice extreme event, extreme sea ice variability, will lead to weaker CO2 ocean uptake, heat and carbon uptake, an increase of CO2 in the atmosphere, warmer temperatures, and that will feed back to even more AMOC decline. And also the subpolar gyre will shut down the convection. There will be less transport of AMOC, weaker AMOC, and therefore less transport, less salt advection feedback coming in from the south, warm and salty waters coming in from the tropics. That would help revive the AMOC. In this particular case, they are feeding back to the AMOC decline. Now, these are not unique results. It has been pointed out in more recent studies that CSM model version 2 seems to have such divergent states, not in AMOC, but they are expressed in sea surface temperature. Their AMOC response to this divergence of sea surface temperatures in the North Atlantic subpolar gyre is quite large, but the AMOC response to this large divergence of sea surface temperatures is very weak. So there's not a very strong connection between what the AMOC is doing versus the surface freshening, the surface warming. This happens in that model mainly in the Labrador Sea, and we can see that already the mixed layer depth, even though it gets deeper, it doesn't get deep enough to be able to explain this kind of, to be able to lead to significant AMOC changes. It's also the mechanism behind this bifurcation has been identified in other simulations. I think this is again with the CSM model, where sea ice variability and AMOC weakening in the subpolar gyre are very tightly linked. In one case, where the CO2 is being increased very rapidly, it will lead to more sea ice growth, and that will lead to a further AMOC weakening. Whereas in the other case, when the CO2 is increased in a slower rate, even though it reaches the same levels of CO2 in the atmosphere, it's not able to weaken the AMOC further because it doesn't allow the sea ice buildup in the subpolar gyre. So the sea ice growth and export in the subpolar gyre is a critical mechanism that is not well represented in all models because sea ice dynamics is a very hard. It has a lot of biases, a lot more biases, but we know that we should be addressing these biases if we want to get a tighter link between AMOC and atmospheric feedbacks, which may be responsible for the AMOC weakening. Now, I will finish by making a juxtaposition between our experiments and typical hosing experiments. We've done some hosing experiments where we imposed different amounts of fresh water in the subpolar gyre, 500 gigatons per year, 2,000 gigatons per year, 5,000 gigatons per year. This is more, I think something like what René showed before in his slides. This is more something like what we would expect if the mass balance of land ice over Greenland was to be melted. So with realistic hosing experiments, similar to what Greenland freshwater would give us, we do not see any weakening of the AMOC. It's only a less than 1 Sverdrup. But in the case where we have a very strong freshening in the North Atlantic, then we see up to 15 Sverdrups weakening in in Greenland in these cases. But as I said, again, we have to put too high values of freshwater perturbations. So looking at the IPCC figure, where what different models are doing, they all are putting so high values of freshwater in order. This is our model here. The results I just showed you. These are other models. They are all putting very large amounts of freshwater in the subpolar gyre in order to get the AMOC to collapse, and that is something that we need to address as a community. Why are our models not able to show the effect of Greenland melt, for example, to the AMOC? Maybe they're not supposed to show it. Maybe it's not only Greenland melting. In our case, where this freshwater transport term that I described earlier, if we quantify it, which is not, of course, apples to apples, I have to point out, if we have to quantify that amount of fresh water that comes through these perturbations, it's actually much smaller. It's cumulative of the order of 0.14 or 0.11 or 0.27 in the different experiments, but really the actual terms is like 0.01. So it is actually an order of magnitude less than what the IPCC models with hosing experiments are showing. Again, I have to point out that this is not apple to apples comparison, but it might be able to point out to the fact that Greenland melt alone, represented as hosing in our models, is not enough to show to get the AMOC to collapse, because we are lacking some of the feedbacks that are present in these simulations, and they are actually amplifying the effect that even the small amount of freshwater flux can have to AMOC. So my conclusions: the AMOC can collapse due to external forcing, warming, and freshwater inputs. It can also collapse due to internal variability, amplified feedbacks, and greenhouse forcing. So the system's stochasticity can be able to impose an AMOC collapse. The global impacts, I didn't show this, but the global impacts are somewhat different if we get collapse because of greenhouse forcing alone, for example, in the 370 or 585 scenarios, versus if you get collapse in a lower scenario with lower global warming level due to internal variability. And the models, and the critical question is, are models too stable, or are we not capturing all the feedbacks in our hosing experiments? Have we tuned the models, the ocean models, to be stable, or is it our RC interaction that's not well represented in hosing experiments? And lastly, the AMOC stability and its repercussions are not fully understood yet, and there is a lot of work to be done in order we are able to represent these effects well in our models and make estimates about tipping points and how imminent tipping points are. Thank you for your time.
Thank you so much, Anastasia, for such an excellent talk, which I think it complements very nice the first presentation by René. So now we are moving on to the discussion session, and we are taking questions for both speakers. So I've been checking the questions, and the first question I mean, the most voted question is it's a question by Danielle, and it's what are the most important remaining sources of uncertainty and presumably reasons for scientific dispute regarding the likelihood of or potential of an AMOC collapse in the next 50 to 100 years. I think that Anastasia already talked a bit about sources of uncertainty, such as stochasticity and variance in CIs, for example, or not consider feedbacks. I don't know if you would like to comment more on this, Anastasia, and then we move on to Renee.
Yes, the only thing that I would like to add here is that stochasticity can make the AMOC collapse even at earlier thresholds than the IPCC has talked about. And that's why we should be able to aim to figure out how we can get that better represented in our models.
Renee.
Oh, yes. So I think it's a very interesting question. And I think maybe we need to shift a little bit the narrative of this question because given the time scale of a full collapse, it takes more than 100 years. It is not very likely that we reach a collapse state within 50 years. So I think the more interesting question, what is the probability of finding the onset of an AMOC tipping event before 50 years or in the upcoming 100 years? So, and that is of course still a question, and that really depends on biases and how you force a model, and yeah, understanding all the different mechanisms which are crucial for the AMOC tipping event to happen.
Thank you. And adding up a bit to this question, part of the uncertainty is added up by not considered feedbacks or feedbacks that we still don't understand. And I don't know if you read a recent paper by John Baker that came up 1 month ago that talk about a mechanism that could enhance the resilience of the AMOC to a potential tipping event. I don't know if you had considered or had seen or have some thoughts on that feedback, if you have seen something in your models.
Yes, I think the John Baker study is very interesting, and we're also very intrigued. So we are currently also seeing whether those kind of PMOC, so that is the Pacific Meridional Overturning Circulation, also starts to appear in our simulation. Because we have the quasi-equilibrium simulation, so we can do a very nice and clean experiments to see how it develops. But unfortunately, we have no results yet, so we're currently crunching the numbers.
Okay.
Yeah, and with regards to us, I had looked at how the PMOC is changing in these different simulations, and I didn't see significant change. And most of the change is isolated in the Southern Ocean, which compensates changes in the AMOC. But I didn't in our model simulations. I had not seen. It is in my plans though to go back and look at more scenarios. Yeah.
Thank you, Beth. We are moving on to the next question, and it's a question by Frank, who says, in terms of consequences, what would be the difference between an AMOC weakening and a total collapse, and who or where would be the most impacted?
Yeah, do I go first or?
Yes.
Yeah. So I think there are, if you only consider, for example, the PI conditions, so without climate change, you see, of course, that there are a lot of regions which are struck, for example, the Amazon rainforest, but also Northwestern Europe or the total Atlantic sea level rise, which is increasing. So it is mainly affecting the Atlantic basin and surrounding regions. And of course, if you then also add climate change on top of that, then the whole picture can shift, because sometimes you are expecting cooling under an AMOC collapse, but then the climate signal is becoming stronger. But with our recent analysis, Northwestern Europe is one of the most impacted regions here. But it has a planetary impact, so also keep that in mind.
Yes, I want to also note the sea level changes. These are going to be significant, and we see them also in our simulations. One other thing I want to point out, in simulations where we have housing experiments alone, we don't always get both of the halosteric and the thermosteric effects equally well represented. And that is another area where we want to be, and these two can compensate each other in sea level change. And that is something that it will be very interesting to be looking at in simulations. Ecosystem collapse, as particularly fisheries in the North Atlantic, they are very important. And that, of course, monsoon patterns in tropical regions like in Africa and Southeast Asia.
Thank you. To add up a bit to this question, we have seen from your presentations very extreme impacts in case of an AMOC collapse. How does that compare with an AMOC weakening? Let's say only if AMOC stays or remains in an on state but weakened. Do you know what's the difference of those impacts, or?
Yeah, so if you look at the weakened states, for example, only by 30%, you can still offset, for example, the regional warming over northwestern Europe, but the impacts are less. And when the AMOC does recover, then you see that those like these negative anomalies in temperature will also disappear again when the AMOC starts to recover. So a small weakening of only 30% can already impact certain regions, and of course, with further declining AMOC strengths, those responses become worse.
Yes, and I would add to this also that the timescales are also important. Weakening over how long of a period, because then you have other feedbacks and adjustments taking place in the Earth system. And so this is, it is, but it will be definitely a world that will be different than what we know.
Thank you. Now we have a sort of a different question about your experience communicating this research to people in government. And Marcin is asking have you come up with a simple story that they can understand? And what is the typical response? We can ask first, Anastasia.
Yeah, well, I work for the government, the US government. So it's not very easy to communicate, especially these times, climate change and the urgency that some of the frameworks require, like, for example, tipping points. Tipping points can be very how to say, scary to people, or perhaps and perhaps counterproductive sometimes, because they feel powerless if we communicate things in a very in sort of a dark light. But rather, I have noticed that it's very crucial even to government people to discuss early warning signals, meaning what could we understand from the Earth system to be able to know whether we are moving, or whether we are getting closer, or we are moving towards a state where the AMOC could collapse, or any other of the tipping elements of the system could tip. And I think this is a much more hopeful, because it gives people, first of all, the faith in science, so that science can tell us, can warn us, and feel, in fact, more safe when we talk to them about we are trying to understand in how these things could happen in advance.
Thank you.
Yes, and I've also have experience with communication with the government. So I also work for half a year now at a governmental institute, and it is really difficult now to communicate this paper we were writing about that the temperature is under climate change is declining instead of rising. So that will change the narrative. And it is sometimes quite difficult to explain that to people, and they become, of course, quite skeptical, because they say like, "Oh, you climate scientist, you always said that it's going to warm and now it's going to cool," and so communicating this in a very straightforward way with the public is kind of difficult, and therefore we should be very clear and say that this is a potential scenario, and not only focusing on temperature. So I'm also very happy that we made a lot of progress with the precipitation impacts as well, because now you can have indeed that it may cool under climate change, but that's not the whole picture, right? We also have this drying over the northwestern Europe. And on top of that, we are also having more sea level rise. So only looking at one kind of climate quantity doesn't tell you the whole story. So we now have more evidence for that with additional analyses. But it remains a very tricky question if you only solely focus on temperature.
Thank you, Renee. And
I want to say one more thing here. Also, that sometimes people, especially people who live in at high latitudes, they feel that climate change might be beneficial for them because of the warming and better conditions, etc. And so our studies show that in fact, climate change has a very large degree of change from everything that is normal to the point that we cannot handle it as societies. And I think that is something we want to communicate to people who feel that, oh, we are going for them, it's getting better, but it might actually get worse.
Yeah, and the worrying increase in extreme events as well.
Exactly.
Yeah, thank you both. And now we are moving on to a more sciencey question. And it's from Martha to Anastasia saying, thanks for an interesting talk. Your work shows that the feedback with sea ice is very important in AMOC decline collapse states. Can you comment on how the sea ice extent in the historical simulations in the GIS model compares to observations?
Yes. It's not, so we have a little bit more sea ice. I could send you exact amount, exact description later. Martha, thank you for your question. And actually our melt season seems to be a little bit later than observed, but the seasonal cycle is acceptable. It doesn't have anything extraordinary, and that shows because even up to 2100 our model is very much what all the other models is doing, but at extreme and levels of warming, and also where we have reversal of warming, right? And remember, when we have reversals of greenhouse gases, we have non-linearities added to the system. Our model responds with building up more sea ice when it is in this when internal variability can be large, and it can overcome the warming which tends to melt the sea ice.
Thank you. And maybe we could extend this question for Renee, and how good your freshwater forcing reflects the expected forcing or the expected freshwater input from.
No, yeah, that is really biased, and that is a way too strong freshwater flux forcing. And that is the annoying thing with those climate models in general. They have like these very strong biases. And to get your AMOC in a correct sensitivity regime, you need to add a tremendous amount of freshwater flux in the first place. So it is somewhat unrealistic, and we are also very frank about that. But at least now we are getting two different kind of outcomes under climate change. So it is a first not a very ideal setup, but it really also helps us to understand the different kind of processes that's going on. So it is very valuable. But of course, we hope with the GIS results that you can actually have different kind of AMOC trajectories without any freshwater flux forcing, as Natasha showed with under the SSP 2.45.
Yeah, thank you. Okay, now we are moving on to a question which is also a matter of scientific debate. It's why do not all models on average reproduce the observed cold blob? Do you have some thoughts on this?
Yeah, I think it's like 50-50, like 50 models, or like 50% of the models that they do show the cold blob, and the other 50 they don't. So if you combine them into the multi-model mean, you don't see any cold blob. So it is not reproducing what we see with observations. So it really depends on which model you're looking at. And if you also look at the spreads between all the different models, there is this huge spread going from like 10 Sverdrups AMOC strengths up to 25 AMOC strengths. And we also need to work as a community to reduce those biases, because we know, of course, the AMOC strength, and it really says that we need to fine-tune our models even better.
Mm-hmm, mm-hmm.
Yeah, thank you, Renee. Do you want to comment something, Anastasia?
No, I agree. I'm covered. Let's take more questions.
Great.
Yes.
Great. So there is another question by Tom Harris, who asks, who comments that the Bjerknes Center reports changes in the Nordic Sea, where deep water formation used to stay north of the island Scotland Ridge, but now flows into and contributes to the AMOC bottom water. This could be sufficient to meet the Southern Ocean pool. If so, what will this mean for the Gulf Stream and heat transport? René, you have.
Yeah. I think this is a very interesting question. So what we see that usually in the Ermeringer Basin and the Labrador Basin, our deep water mass transformation, they go to zero, so they don't contribute to that anymore. But there is still a small residual in those specific regions in the Nordic Seas. So they can contribute to your AMOC deep water formation, but it is I didn't do it in all detail, but it is too weak to maintain a full adiabatic AMOC. So your AMOC becomes quite diffusive, and you'll only see a very small residual AMOC, which is less than 5 square drops. So it can contribute to that. There are maybe some adiabatic pathways, but like the full characteristics of an adiabatic AMOC, they just disappear. So yeah, it becomes a collapsed / weakened AMOC.
Thank you.
Yeah. Yes, and I think that the models, especially models of low resolution like our model, they don't represent very well this connection between Nordic seas and the AMOC. Definitely, this is the lower branch of the AMOC, but we don't have it. Higher resolution models presumably will play a role, and maybe perhaps this is the reason, one of the reasons that they have so higher, they tend to show higher AMOC strengths than the low resolution models.
Thank you. Very interesting. Yes, the role of the Nordic Sea overturning or deep water formation there. Yeah, in the AMOC strength. Yeah.
And if I may add to that question, so following up from Natasha, so we now have the high resolution model, so with strongly adding oceans, and we see some very interesting features happening in the Nordic seas. So they probably also contribute to this Nordic, this deep water formation. And there we have the deep, the overflows better parameterized compared to the low resolution model, but we need to figure it out in much more detail.
Yes, I don't know if it was in your models, but in some other models that I have seen high resolution, they get more Nordic convection, but because it is too deep, it cannot get over the seal to be So there are a lot. There's a lot of complexity there.
Yes, I agree. Yeah.
Thank you. And this takes us to the next question, actually associated with ocean model resolution. So Peter Van Thienen is asking that 3 years ago, is commenting that 3 years ago, Helen Hewitt wrote how about ocean model resolution is insufficient for adequate simulation of all relevant processes. And how has this evolved since then? Since 3 years ago, I mean, yeah.
Yeah, or I think there have been great steps in getting like these AMOC tipping dynamics now with sufficient high resolution, like a 1 degree ocean resolution and also a 2 degree atmosphere resolution. So there's a typical CMAP 5, CMAP 6 standards where we now show that. And also with this paper published yesterday from our group, that we also show it in an open 1 degree ocean resolution. So there have been a lot of steps, and we hope that also other modeling groups will do the same kind of experiments with even higher resolution, because with a higher resolution, you will resolve much better the processes like eddies, which are of course very important for the salt budget as well. So yeah, there have been steps in the past 3 years.
Yes, I think resolution is one of the things that we want to go definitely towards. I mean, it's just increasing resolution in the boundary currents, in the topography, everything is the seal width and size, the strait size, it's very important. But better sea ice models, obviously, and better air-sea interaction parameterizations for the feedbacks that I talked about. So it's not just, there's not only one way that we need to improve our models.
Yeah, that's true. Well, we have another question. We have some technical questions as well, and this one for Anastasia from This person says, thank you for the interesting talk. What effect do you think the biases in the GIS model have on the stochasticity and probability you get? If I am correct, the GIS model is known for having a too strong and biased AMOC.
Yes. We do have very strong AMOC, and for that reason, we have the strongest decline, stronger than average models decline. And so that is one type of bias. Second bias is we don't have overflows. We don't simulate well the overflows. And maybe that's why we have a shutdown of the AMOC in our models at high scenarios where we don't capture the high latitude convection regions. Well, we also, but in terms of stochasticity, that is also another issue. We have internal variability, the climate internal variability, modes of variability like ENSO, PDO, things like that. They are well represented in the model. Perhaps we have a little bit too strong internal variability in terms of AMOC, for example, in terms of ENSO, and that adds to the stochasticity that is imprinted at high latitudes, obviously. And also our AMOC has a larger variability than the average other models that I have seen. So these all add, but I wouldn't necessarily say that they are problematic. Perhaps they might reveal some aspects of the system which are not captured by other models. So maybe so model bias is not always, we might get lucky for the wrong reason, basically. Yeah.
Yes,
that's,
thank
of
you.
course we have to correct the biases. Yeah.
I think that we have time for one more question, and this is by also an anonymous attendee. It is, do I understand correctly that on the one hand, some climate models show AMOC collapse on the realistic forcing, for example, 2 to 2.5 degrees of warming, but on the other hand, to see AMOC collapse in housing models, you need to introduce unrealistic forcing. Why?
So the AMOC is simply set too stable, so meaning that the salt advection feedback is actually stabilizing your AMOC. And to get this destabilizing feedback to be active, you need to add a unrealistic amount of freshwater flux forcing in the first place. And then you are in the stable regime, and then you are having a more sensitive AMOC and is more prone to tipping. But of course, we know that this FOVS parameter I've talked about in the first place, we know it from observations at 31st South, which are conducted over there. So we know where it goes wrong, and now we need to fine tune our models even better. And I expect to see that if we are in a correct sensitivity regime, we will see more AMOC tipping events happening in the next generation of climate models like the CNOP 7 models.
You're ready. Yeah.
Yeah, I agree with exactly what René said, and I would add only the fact that we also need to have a better representation in the models and in the housing experiments, the feedbacks, the local high latitude feedbacks that undercut or push back the salt advection feedback.
Great. Well, I think that we can wrap up the discussion here. Thank you so much both for your great talk and answering the questions, and all of the attendees for the great questions. And now, with a few minutes remaining, we want to give a round of applause and thank our speakers again for their excellent presentations and for answering all of our questions. And also many thanks to all of you that are still online for your attention and participation today. And we also want to invite you to attend our next event in May, 21st of May, I think, and it will focus on the implications of AMOC tipping. You can find the link in the chat. Have a lovely rest of the day. Thank you.
Thank you very much, everyone.
Thank you so very much for all your questions.
Thank you all. Bye-bye.
Bye.